Okay, thank you, Chairman. And also, I'd like to thank organizers and all the staff members of this conference for accepting my online attendance, as well as for giving me this time to give a talk on my recent work. So my voice is okay, no problem.
Yeah, it's okay. We can hear you.
Okay. So today I'd like to talk about the isothermal compressibility and effects of three-body molecular interaction in a strongly interacting ultracold fermiatomic gas. So my name is Yoji Ohashi from Keio University in Japan, and these are my collaborators. So who are all my current or previous PhD students. So just before starting, I should say where I am now. So actually I'm here. So maybe most of you are here, and maybe I'm on the edge in this picture. So time difference between you and me is just 3 hours and 30 minutes. So I should say good afternoon to you, but you should say good evening to me. So anyway, online talking is sometimes inconvenient, especially on discussion because of so sometimes time lag or freezing or occurs, and sometimes so voice quality becomes low. But in any event, so I hope you enjoy my talk. So from now about 30 minutes. Okay, coming back to the front page. In this talk, I first give somehow detailed introduction about my research field, as well as the background and motivation of this work. So why isothermal compressibility? And then I explain the theoretical formulation and then show recent results. Okay, my research field is ultracold film gas physics. So in this field, film atoms such as lithium-6 and potassium-40 are trapped in the magnetic or optical potential, and they are cooled down to below microkelvin. So in this low temperature region, various quantum many phenomena occur, and the superfluid phase transition is a typical one. So this left figure shows the first observation of the superfluid phase transition in the potassium-40 film gas in 2004, done by Gira group. So in this experiment, atoms in these two atomic hyperfine states are trapped, and the Cooper pairs are formed between them, as in the case of metallic superconductivity. And in this figure, this axis shows the temperature normalized by the Fermi temperature TF, and this axis shows the external magnetic field. But physically, this axis means the strength of a pairing interaction between these Fermi atoms contributing to the Cooper pair formation. So the decrease of the magnetic field corresponds to the increase of the pairing interaction. And this axis shows the number of Bose condensed Cooper pairs. And in this experiment, the non-zero value of this quantity means the system is in the superfluid phase. So in this temperature magnetic field plane or temperature interaction plane, Tc is around the sky blue area here. So with decreasing the magnetic field or with increasing the strength of the pairing interaction, Tc increases like this, and it approaches a constant value around here. And the maximum Tc is obtained around here, which amounts to about 0.2 in unit of Tf. And this value is much larger than the case of metallic superconductivity. And to understand this film gas superfluid, there are two keywords. One is a Feshbach resonance, and the other is a Bcs-Bec crossover. In a Feshbach resonance, two Fermi atoms form a K-psi molecular boson, and it dissociates into two Fermi atoms again. And here, this molecule is different from Cooper pairs, but rather close to a chemical object. And when we describe this process by using this diagram, so we can obtain an effective interaction between these two Fermi atoms, given by this. And here, G is the coupling constant of a Feshbach resonance, and 2 nu is the energy of this molecule. And experimentally, this 2 nu can be tuned by an external magnetic field, so this interaction is also tunable. And this tunable interaction has already been observed in various cold Fermi gas systems like this. And in particular, so this pairing interaction becomes very strong when 2 nu becomes very small. And using this tunable pairing interaction, the Bcs-Bc crossover has been realized, where the character of superfluidity continuously changes from the weak coupling Bcs type discussed in metallic superconductivity to the both Einstein condensation of tightly bound molecules with increasing the interaction strength. So this figure shows the so-called Bcs-BEC crossover phase diagram of ultracold Fermi gas in terms of the temperature and the interaction strength measured in terms of the inverse scattering length AS normalized by the Fermi wavelength KF. And in this scale, negative side corresponds to the weak coupling Bcs regime, and the positive side corresponds to the strong coupling BEC regime. And as I explained, in the superfluid phase, we can see how the Fermi superfluid continuously changes to the both superfluid with increasing this interaction strength. And not only the superfluid phase, so we can see interesting physics above TC. So the normal phase is divided into 3 regions. So normal Fermi gas regime, fluctuating preformed pair regime, and both gas regime. But of course, the boundaries are not phase transition, but only crossover. And because of this situation, even above TC, we can examine how atomic Fermi gas changes to a molecular Bose gas. So in the study of Bcs-Bc crossover, we usually start from the weak coupling Bcs regime to examine how atoms change into the molecules. But of course, as an alternative approach, we can start from the strong coupling regime to see how molecular gas come back to the atomic gas. Of course, this research direction is somehow a personal taste, but even so, starting from the strong coupling regime, we can see a very interesting physics. So to see this, okay, let's start from the extremely strong coupling BEC limit, where all the fermions form tightly bound molecules and they never break up. So in such a situation, the internal structure of each molecule is no longer important, and we can treat the system as the ideal Bose gas. And still starting from this extreme case, when we gradually decreases the interaction strength, so virtual dissociation and the reformation of these molecules start to occur. And when the interaction further decreases, this kind of particle exchange between 2 molecules start to occur. So, and physically, this means the effective interaction between these 2 molecular bosons are mediated by these 4 unpaired Fermi atoms. And this process is diagrammatically given by this. And when we further decreases the interaction strength, so this kind of particle exchange start to occur among these 3 molecules. So again, this process can be interpreted as an effective molecular interaction, effective 3-body molecular interaction, where interaction is mediated by 1, 2, 3, 4, 5, 6 unpaired Fermi atoms, and diagrammatically described by this. So in principle, when we further continue this discussion, in principle, we can reach this kind of situation. So there exists even a 10-body or 100-body molecular interaction. But of course, in such a regime, the molecular picture is no longer good. And in this case, it is better to treat the system as an interacting Fermi gas. So this is just a weak coupling BCS regime. But anyway, starting from BCS strong coupling regime, one interesting issue is to appear the appearance of this kind of multi-body interaction between tightly bound molecules. And to examine these multi-body interactions, isothermal compressibility is a useful quantity. So to explain this, so in this figure, this blue line shows the temperature dependence of the isothermal compressibility in an ideal Bose gas, not a Fermi gas, ideal Bose gas. So in an ideal Bose gas, it is well known that this quantity diverges at Tc. But this divergence is suppressed when the repulsive interaction works between both atoms. And even at Tc, then the value converges, and which is proportional to the inverse repulsion between both particles. So this result means isothermal compressibility around T Bose-Einstein condensation temperature is very sensitive to the Bose-Bose interaction. Then we can also expect this kind of sensitivity even in strongly interacting Fermi gas, where the system properties are dominated by tightly bound molecules. And also, I briefly mentioned that so multi-body interaction, especially a three-body interaction, is also discussed in other research fields. One example is nuclear physics. So so-called Fujita-Miyazawa type three-body interaction has been discussed, which is mediated by pion as well as the delta particle. The second example is the neutron star physics. So in this field, three-body interaction is considered to be a possible origin to stabilize the very massive neutron star, which has recently been discovered. And this problem is sometimes referred to as the two solar mass problem. Okay, so keeping this background in mind, so in today's talk, I theoretically discuss the isothermal compressibility in the normal state of an ultra-cold Fermi atomic gas, and within the framework of the self-consistent T-matrix approximation, SCTMA, so which is one of the standard Bcsbc crossover theory, we clarify how the two-body and three-body molecular interaction can be seen through the thermodynamic quantity in the Bcsbc crossover region. Okay, now next I explain the outline of the formulation. So in potassium-40, in the case of potassium-40 and lithium-6 Fermi gases, so it is well known that the system is well described by the simple Bcs Hamiltonian here. So Bcs Hamiltonian consists of the kinetic term of fermions and the pairing term between the Fermi atoms. And here I emphasize that in the Bcs Hamiltonian, there is no interaction between Cooper pairs. And in this Hamiltonian, C describes the Fermi atom, so creation operator of a Fermi atom with pseudospin sigma, which describes the two atomic hyperfine states contributing to the Cooper pair in this system. And the pairing interaction U is assumed to be tunable by adjusting the threshold energy of a Feshbach resonance. But in the theoretical calculation, we simply treat it as a tunable parameter. And in cold Fermi gas physics, we usually measure the strength of a pairing interaction by using the scattering length AS, so which is directly related to this bare interaction U by this equation. And as I explained, so in this scale, so negative side corresponds to a weak coupling regime, and the positive side corresponds to the strong coupling regime, and the intermediate coupling regime is sometimes referred to as a unitary limit, so which is the diverging S-wave scattering length, which is given by the diverging S-wave scattering length. And in this model, we examine effects of pairing interaction through self-energy correction involved in the single particle Green's function. And in the framework of the self-consistent T-matrix approximation, SCTMA, this self-energy is diagrammatically given by this. Here, the double solid line is a Dress-Green's function. So here, involving the self-energy correction. And the gamma here is constructed by the summation of this kind of ladder-type diagram. And physically, gamma describes the pairing fluctuation by strong pairing fluctuation, where the formation and the dissociation of this kind of Cooper pair, preformed Cooper pairs, repeatedly occur. And in the strong coupling BC limit, where this kind of dissociation does no longer occur, gamma is reduced to the Bose-Green's function, so describing the molecular propagation. And in this SCTMS scheme, superfluid phase transition temperature, TC, is determined by the Thouless criterion, which states that the superfluid instability occurs when the particle-particle scattering matrix has a pole in the low energy and low momentum limit. And actually, so in the Bcsbc crossover region, the chemical potential, so Fermi chemical potential is known to deviate from the Fermi energy epsilon F. So because of this, we actually solve this TC equation together with this number equation to self-consistently determine TC and the chemical potential. And this figure shows self-consistent solutions for TC and the chemical potential at TC as a function of the interaction, pairing interaction. And in this figure, we find TC first gradually increases with increasing the interaction strength, but it approaches a constant value as observed in the potassium-40 Fermi gas. And in the BEC limit, the TC approaches Bose-Einstein condensation temperature of N/2 ideal Bose gas, because here all the Fermi atoms form tightly bound molecular boson, and the superfluid phase transition is simply described by the Bose-Einstein condensation of these tightly bound molecules. And in this figure, so we find the chemical potential gradually deviates from the Fermi energy epsilon F and eventually becomes negative in the strong coupling regime. So this is also a typical Bcsbc crossover behavior of this quantity. And once these quantities are determined, so isothermal compressibility is conveniently calculated from this thermodynamic identity, and it is diagrammatically given by this. And here, 3-point vertex lambda is chosen so as to be consistent with SCTMA self-energy, and the resulting diagrammatic equation is given by this. And by solving this equation, we determine isothermal compressibility. Okay, next show, I show our results. So this figure shows calculated isothermal compressibility in the BCS-BEC crossover regime of an ultra-cold Fermi gas in the normal state above TC. So in this figure, we find in the whole interaction regime, this quantity monotonically increases with decreasing the temperature, but it still converges at TC. In particular, the convergence in the strong coupling regime around here implies the existence of repulsive interaction between Cooper pairs. And to confirm the validity of this calculation, so we compare our result in the unitary limit with a recent experiment on lithium-6 Fermi gas. The result is here. So experiment data is this green circle, and SCTMA result is this red solid line. And the calculation is in the unitary limit. So we immediately find the calculated isothermal compressibility well explained the experimental data. So in this figure, this blue line is also a theoretical result by using a different strong coupling theory, which is called TMA, T-matrix approximation. So in this another strong coupling theory, it is known that the interaction between the preformed Cooper pairs, tightly bound molecules, is completely ignored. So because of this, this calculation, this theory always gives a diverging isothermal compressibility at Tc, as in the case of ideal Bose gas. So because of this, TMA always overestimate this quantity near Tc. So this is a basic numerical result. And next, to discuss how the molecular interaction appears in this thermodynamic quantity, we focus on the temperature dependence at interaction dependence at Tc. So this figure shows, again, calculated thermodynamic isothermal compressibility, but at Tc as a function of the interaction strength. So starting from the weak coupling regime, this quantity is found to be, so first increases interaction strength. But this behavior can be easily understood as a ordinary behavior in weakly interacting Fermi gas. Because when we evaluate this quantity in the presence of the attractive interaction within the random phase approximation, we obtain this expression. And from this, we find attractive interaction always enhances this isothermal, enhances this quantity in the weak coupling regime. But this figure shows that this increase is not monotonic, but exhibits a hump structure around here. And to see what's happening around here, so this lower panel shows interaction shows a number of stable molecules appearing in the system as a function of the interaction strength. So from this lower panel, we find, so around the hump structure, the number of molecules, so tightly bound molecule rapidly increases, and the molecule dominate the system around here. So this means, roughly speaking, the left side of this hump structure may be viewed, so the left side of this hump structure, the system may be viewed as an atomic Fermi gas. On the other hand, right side of this hump structure, so the system may be viewed as a molecular Bose gas. So molecular interaction is expected around here. And from now, I focus on this region. And to see how the molecular interactions affect this quantity in this regime, so there are two key issues. So one is how the STTM gives a molecular interaction. And the second key issue is how the Fermion isothermal compressibility calculated in STTMA continuously changes to the boson isothermal compressibility. So from now, I briefly explain these two issues. So first, the first key issue is, so because SCTMA uses a Dress-Green's function involving the self-energy everywhere in the diagram, this particle scattering matrix gamma, which physically gives a pairing fluctuation, or the Bose-Green's function, has this kind of diagram, and where this self-energy correction comes from the Dress-Green's function. And when we deform this diagram without changing the topology, so we obtain this kind of figure, diagram to figure. And we simply regard the shaded region, so gamma, as a molecular Green's function. So this diagrammatic structure is just the same as the Hartley self-energy in interactive Bose gas here. And here, this is interaction between boson. And the comparison from this and this, we find this Bose-Bose interaction is mediated by these 4 unpaired fermion in this diagram. So which is just the same as this 2-body molecular interaction. And when explicitly evaluate this part, we obtain this one. And here, molecular interaction AB is given by 2 times atomic interaction, and this is positive. So this means this effective interaction between molecule is repulsive. So the second issue is how the fermion isothermal compressibility changes to the Bose isothermal compressibility in the Bcsbc crossover. So to see this, so it is convenient to repeatedly substitute this 3-point vertex into this diagram describing this isothermal compressibility. Then we find that this kappa T involves the series of this kind of series of diagrams here. And among them, so we consider the first one. And in this diagram, when we simply replace gamma by a molecular Bose-Green function and simply regard this triangular structure by a kind of vertices. So this one is found to just the same diagram giving the Bose isothermal compressibility in the lowest order. In addition, so in the second and third one, so we see the effective molecular interaction mediated by 4 unpaired fermions here, here, here. And using the same replacement, the gamma by a Bose-Green function. For example, the second diagram is also given by this. And summing up these series, we obtain the random phase approximation type, so isothermal compressibility, but in the boson case. So although we start from the fermion isothermal compressibility, so we automatically obtain the boson isothermal compressibility in RPA, within the RPA in the strong coupling BC regime. So, but when we, and the result, we obtain this one, but when we simply plot this one in this figure, so we find we cannot explain the calculated isothermal compressibility. So the difference comes from the 3-body contribution. So then the next problem is where, from where we can obtain the 3-body contribution. To see this, I point out that so SCTMA kappa T isothermal compressibility also involve this kind of diagram. And again, we replace gamma by a Bose-Green function in the strong coupling regime. This diagram can be written like this. And this part corresponds to this hexagonal structure. Then we immediately find this one is directly related to the 3-body interaction, where 2 external lines are connected to each other like this. And when we explicitly evaluate this diagram, we obtain this result. So this case, this interaction is attractive. And so summing up this kind of diagram, so corrected isothermal compressibility in effective Bose molecular gas is obtained this. So in addition to the previous 2-body repulsion, now 3-body attraction appear here. And when we plot this one in this figure, we find, so this will explain the calculated isothermal compressibility in SCTMA in the strong coupling regime. So from this, so this difference comes from the 3-body interaction effect. And usually in the Bcsbc crossover physics, strong interaction between fermions is focused. But our result indicate besides this, multi-body interaction between tightly bound molecule or tightly bound preformed Cooper pair is also an interesting topic in ultracold Fermi gas. Okay, to summarize, so we have today we have discussed isothermal compressibility in an ultracold Fermi gas within the strong coupling SCTMA scheme we show that besides the two-body molecular interaction, the three-body interaction, molecular interaction, is also crucial for the thermodynamic quantity, especially in the strong coupling BC regime. So, and finally, so far, I have ever attended in-person international conference held in India, so 2 times. So this time, unfortunately, I cannot attend, so I can only have online attendance, but I hope next time I can meet you in person. So thank you for your attention.
Thank you, Professor Ohashi. And this talk is open for questions. We have some time for questions. From the audience, is there any question?
So I have a question. So
Okay.
when you are discussing about this phase-back resonance, you are tuning this S-wave scattering length AS with
Yes.
the magnetic field,
Yes.
but your system is fermionic.
Yeah.
And so, I mean, is it the S-wave or it should be the P-wave?
No. Maybe we are selectively using S-wave scattering length. In this case, even under the magnetic field, S-wave pairing only occurs because, okay, in the electron case, for example, under magnetic field, upspin electron increases and downspin electron decreases. But in the case of ultra-cold Fermi gas, the number of upspin, also pseudo-spin up Fermi atoms and pseudo-spin down atoms are fixed. So even under magnetic field, a spin balance doesn't occur. Because of this, for a given S-wave interaction, S-wave superfluid only occurs. But of course, we can choose P-wave festival resonance. Then a P-wave superfluid is in principle occur, but experimentally it hasn't been realized.
But we in general says that the fermions do not have the S-wave scatterings.
No, but we are considering 2 components. S-wave scattering works between up and down fermions. So we assume S-wave interaction works between upspin Fermi atoms describe upspin, pseudo-spin up and pseudo-spin down. Actually, let's see, experimentally, for example, in potassium 40, let's see, S-wave interaction works between these 2 hyperfine states. Because the hyperfine states are different, so S-wave interaction works even in the fermion case.
Okay, thank you.
Okay.
So I have a question.
Yes,
Like
please.
two-body, the three-body interactions are like crucial compared to two-body interactions. So then if you go on adding like 4-body interactions or 5-body interactions, they may be also important in your studies, right? So how small those interactions are?
Sorry, pardon me. I mean, somehow sound resolution isn't so good. Would you repeat the question?
You said 3-body interactions are crucial.
Yeah.
So then I can also add 4-body interactions. Then
4-body or 5-body. Okay, that's a very good question. Actually, when we carefully check the SCTMA diagram, you're right. So actually, there are 4-body interaction, 5-body interaction. There are and many body interaction also exist. But the point is, the contribution is a higher order compared to the 2-body and 3-body.
So are you analyzing using some perturbation theory that they are from higher order, or how do you analyze that?
Yeah, I mean, but let me see. Okay, first we note that in the strong coupling BC regime, S-wave scattering length is very small. So AS is a small parameter. Okay. So and interesting point is, let's see. When we evaluate a 2-body interaction, okay, this one, it is proportional to AS, to the first order. And examine the 3-body interaction, again, it is proportional to the AS, to the first order. But when we examine the four-body interaction, we find it is proportional to AS to the fourth power. Because of this, it is exact, but exists, but the contribution is negligibly small in the strong coupling BC regime.
Yeah. Okay, thank you. I got it now. I have another question. So through RPA, you are able to consider self-energy corrections to infinity order. What about vacuum polarization kind of effects?
Yeah. What do you mean by vacuum?
So this through RPA, you are
Not RPA, yes, but the T matrix.
Yeah. So you are only considering self-energy interactions to infinity order.
Sure.
So what about other kind of interactions like?
Okay. Maybe to explain this, we need a knowledge about the renormalization group. Okay, in the present case, so in the present case means attractive fermion, the particle channel is relevant. On the other hand, for example, particle hole diagram is irrelevant. Irrelevant means only a perturbative contribution. Because of this, of course, exactly speaking, particle hole channel also exists. But when the pairing interaction is strong, so particle channel is the most relevant contribution. Because of this, we only take into.
Okay, thank you. Yeah.
Okay.
Thank you. So if there is no more question, let us thank the speaker for the excellent talk.
Thank you.